Okay, I am continuing my physics final exam. So this is my calculus-based first semester physics, and I'm going over the solutions to my final exam. This problem I think is a little bit better than my previous ones. And again, I try to give questions that are, straightforward and not too tricky, and ones that can be solved different ways. And this one can be, and I'm going to solve it every single way that I possibly can. So let's look at the question. So, and I made this up. And at the end, I don't think it was the best numbers, but the idea is fine. So I have Io, the moon of Jupiter, mass of Io, the radius of Io, a spacecraft with a mass of 1,101 kilograms, a velocity vector 100, negative 112, 0, and 3,000 meters above the surface of Io. The spacecraft crashes into Io due to only gravitational interaction, so there's no forces, thruster forces on it. And the question is, how fast would it be on impact? Now, I drew a picture. So in this case, we have if you want to say where does it hit, I didn't ask where. I said how fast was it going, because this is going to do something crazy, and in fact, maybe it doesn't even hit, right? So that was the part of the bad thing. I didn't want to just have it pointed straight down, because I want to emphasize the idea that that it doesn't really matter as long as it hits. The speed. Okay, so I think I did mess up there. But since we don't really care about the time, we care about the change in position from here to the ground, we can use work energy principle. So this is a work energy principle type problem. And the first thing you do when you find a work energy problem is to define your system. In this case, it's going to be the spacecraft plus Io. And by including the moon and the spacecraft in my system, then I can have a gravitational potential energy. So that's my system. There's no external forces on there, so I have work is a change in energy, and that's 0. There's no work done on the system because there's no external forces. With that, I can say, well, what kinds of energy do I have? Well, I have a change in kinetic energy for the spacecraft. I'll assume that Io does not change in kinetic energy. Technically, it does, because the spacecraft will pull on it, but the mass of Io is so much larger than the spacecraft you wouldn't notice any difference. And so with that, I can say the work done is 0, and that's going to be the change in kinetic energy of the spacecraft plus the change in gravitational potential energy of the system consisting of the spacecraft and the moon. So kinetic energy is 1/2 mv squared, and gravitational potential energy is negative g, mass of the spacecraft, mass of Io over r, where r is the distance between them. And I didn't give r, I gave the radius of Io plus the altitude above it. So that would be, in this case, r, the initial r would be h plus r. Okay. So let's go ahead and put that. R1 is going to be equal to h plus r. R2 is when it crashes into the surface, and it would just be r. What about V1? Now you notice here this is v squared, and it's not a vector, and that is a vector. So V1 is going to be the magnitude of V1 vector. So if you want to calculate that, that'd just be the square root of 100 squared plus negative 112 squared plus 0 squared, the magnitude of a vector. The final velocity, V2, we don't know. That's what we're looking for. Okay. So all we need to do is put into this equation. So I'm going to say 0 equals K2 minus K1 plus U2 minus U1. Now, are any of these terms 0? No, they're not, right? They're not, because this is not 0, that's not 0, that's not 0. None of these are 0. So let's just put in all our values, or not our values, but let's say 1/2 m, this is m is the mass of the spacecraft, v2 squared minus 1/2 m v1 squared. Now I have u2 is going to be minus g, mass of Io, m of the spacecraft, over big R. So big R is the radius of Io. And then I'm going to say minus the initial, which is negative of a negative, so it's plus g, mass of Io, mass of the spacecraft, over r plus h. I want to solve for V2. So the first thing I can do is divide both sides by the mass. And this cancels. If I want to, I might want to multiply both sides by 2. That's just for fun. And that way, that cancels, 2, 2. Now let's rewrite the equation. I'm going to now add all these terms to the other side, so I get V2 squared by itself. So I get, I'll write it right here, V2 squared equals V1 squared. Now this is added to the other side, so it's going to be plus 2 mass of Io over r. And that one's going to be minus 2 g. Mass of Io g. I don't know why. Over r plus h. Put that right there. Okay. So now all I have to do is solve for V2. Take the square root of both sides. V2 equals the square root of V1 squared plus 2g mi over r minus 2g mi over r plus h. And now I just need to put that in my calculator. Okay, now let's just think for a second before I switch to my Python calculator, because I do want to do this in Python. No, I'm not going to do that. I'm going to do this first, and then I'll come back if I want to. So I want to show you another way to solve this problem. Okay, so let's switch to Python. So here I have Python open. And I like to use Python as my calculator because, and let's go ahead and put it here, Phys 221 final 3, save. I like to do that because in Python, because it allows me a lot more flexibility in calculating stuff. So let's just go ahead and start putting in some of my initial values. G equals 6.67 times 10 to the negative 11th. And that's how you do scientific notation in Python. You just do E negative 11. Now I need the mass of Io. I'll call that big M. I don't really need the mass. This is called big M. I don't need the other mass. It's going to be 8.9 times 10 to the 22nd. The radius of Io, it's called R, is 1.8 times 10 to the 6th. H is 3,000. The mass of the spacecraft, I don't need to know. Okay, so after that, I can just put in my, now I can literally type in my expression. Oh, V1. V1, watch this, equals vector 100, what was it, negative 112, 0. So I actually enter that as a vector. You can do that in Python. Now I'm going to say V2, I'm just going to type in my expression. V2 equals the square root of V1 magnitude squared. So that's going to be magnitude of V1 squared plus 2 times G times M divided by R minus 2 times G times M divided by R plus H. And that's it. And I can say print V2 equals V2 meters per second. And let's run it. 183. And now let's just compare. Let's say print V1 equals magnitude of V1 meters per second. Just see how much faster it's going. So 150. Okay. So it's going 150. It was going 150. Now it's going 183. So it did speed up. So those numbers are kind of fine. I mean, the only problem with the numbers I had was that it didn't directly necessarily hit. And I could model that later. Okay. But let's look at, there's another way to solve this problem on the final exam. And I'm going to do that for you now. Okay, there's my computer right there. Let's move that out of the way. I don't really have room here. Okay, good. Okay, what if I want to use the momentum principle? So what if I do this? let's say this is v1 and it's headed straight towards that, which it's not. But it doesn't matter, right? It doesn't matter about the final speed. The direction doesn't matter. So I'm going to pick it going straight towards there. So v1 is 150 meters per second. And I want to calculate the force on there. I know that there is a gravitational force. The gravitational force Fg is going to be negative g, mass of Io, mass of the spacecraft, over the magnitude of the distance between them squared, r hat, right? So that means it's going in the, and let's just even call this in the negative x direction. So let's say this is just in the x direction. And so if that's the case, I know this is r, let's call that the origin, and let's call this r plus 3000 is my initial x value. So x0 equals r plus h, and then the force on it is going to be equal to negative g mi m over x squared. I'm not going to use vectors because I'm trying to do this as simply as possible. And that's the only force acting on it, and that's going to be the change in momentum in the x direction with respect to the change in time. Now, if I take a very short time interval, let's say delta t equals 1 second, then I can write this as p2 minus p1 over delta t. I can multiply both sides by delta t and add p1, and I get p2, and this is just in the x direction. p2 equals p1 plus this f delta t. So I can find the new momentum after this short time interval, and this is wrong, but if the time interval is small, then it's fairly good, it's fairly accurate. Okay. Now I can use that momentum and the average velocity. I can say average velocity is approximately p2 over m. That's the mass of the spacecraft. And then I can say that's equal to the change in x over the change in time. Oh, this is going to be v is negative. It's moving in the negative direction. But it shouldn't matter. And I'll change out and show you both ways. So now I can say this is equal to x2 minus x1 over delta t. And if I solve this for x2, I get x2 equals x1 plus p2 over m delta t. Important, important. And then I can update time. T2 equals t1 plus delta t. Important. Now I've gotten the time, position, and momentum at the end of that time interval. I can just go up and do it for position 3. And I can do position 4. And I can keep doing that until x2, x, or x whatever, xi is equal to r. And then I'll stop. And then I'll know what my velocity is from up here. What happened? Did it stop? No. Okay. So let's do that in Python. So I'm switching back over here to Python. I think this is still working. Yeah, it's still working. Okay, let's just open up a new trinket. So I'm just going to say new trinket. Go up here. New trinket. Glow script. Python. Let me go ahead and copy the stuff I have over there from my previous one. I only need this stuff. Let's print that too. Let's copy that too. Okay, now I'm going to go ahead and put my values in there. X equals, my initial x is going to be equal to r plus h. I got that. I do need a mass of the spacecraft, so let's call that ms equals 111. I need my initial velocity, my initial momentum, let's call it. So p equals negative ms times mag v1. That's in the x direction. Now I need my time, t equals 0. My time step, dt equals 0. It's probably 0.1 should be fast enough. And now I'm just going to make a loop. While x greater than or equal to r, do the following. First, calculate the force. So I'm going to say F equals negative g times ms divided by x squared. Next, I'm going to use that to update the momentum. P equals P plus F times dt. Now, yes, P started at some value, and F is in the negative x direction, so it's going to make it go faster and faster. Now I need to update the position. X equals x plus P divided by m times dt. You'll notice here that this is not an algebraic equal sign. This is a make equal to sign. So it says take the momentum, add F times delta T, and make that the new momentum. Just to be clear there. Now update time, T equals T plus dt, and that should be it. And let's go ahead and print V2 equals P divided by M meters per second. And let's see if this works. So let's save this. Phys 221 final 3 version 2. Now there could be an error in here because I did it so fast. And this is live. This is, like doing those magic tricks, right? And there's a problem. M is not, aha, MS. See, I knew there would be a mistake, and I did that on purpose just so you could see that everyone makes mistakes. Okay, I think that's right. Check that out. Check it. Okay, now I did say it didn't matter which way it's going. Let's say that it starts off going in the positive x direction. So now it's going to move away from the asteroid and then back down towards there, and I get the same thing. Okay, so I'm going to link to you both of these codes so you can have them, you can play around with them. This is the Euler method of numerical calculation. It's a pretty legitimate way to do things. It's not cheating. I did have one student use this method on the test, and I was totally fine with that. I told them they could use Python, and that student did, and yay. Okay, so there you go. That is problem number 3.